My name's Matthew. I'm a programmer here at Intrepid. I'm just going to run you through the Geology from Geophysics suite of tools that we have available in Intrepid in the latest version. The Geology from Geophysics tools are essentially inversion tools, so you can use them to turn measured or generated geophysics signals back into geologies. And I'll show you through a couple of the tools we have available that can do this sort of thing. I've got a mouse. So the first one I want to show is Naughty Auto Modeling. So this tool can develop a set of dikes with a dip and strike from a measured magnetic signal. And I'll run you through one of the task examples we have first. So this is in our, there's a shift with every copy of Intrepid. There's task examples like this. So this tool is from the Ebagula data sets we have. And it can turn, if I run this task, I'll show you what it does. I'm assuming you can all see this screen over here. Let's let it run.
Yep, I can see it.
That's good. I'll drag this over. So this is the Naughty tool in action. So it's produced this viewer, and you can rotate it around and show it's actually generated a number of dikes underneath the surface. And you can see the original line data set going across here. And they've each got their own dip and strike, as you can see, calculated here in these little flat cylinders. And these dikes will all be saved out into a separate directory. And if you need to, if you need to access the data directly, it's all available in CSV format, so you can import it however you like. And I'll quickly show you one of the other tools we have. So some of you may have seen the 3D Explore tool being demonstrated by Jason a couple of days ago. In this case, because each of the dikes is exported into a VDP format, we can import those with 3D Explore. I'll show you what that looks like. Just give it a sec to load. So this is what it looks like. You can see each of the individual dikes that was in that previous view are now available to be imported one by one selectively. You can even put get the data set and put it over the top. What's this one? So you can see where the lines are relative to all the dikes, and it's all geolocated into the same space. Rotate it around and have a look at it. That's the Naughty tool. Now that's on scalar potential fields. You can actually run it on potential gradient fields, and that's one of the new big changes that we've had to Naughty Auto Modeling in the latest release. Unfortunately, I can't show you this example. That just recently De Beers has been giving us this example data set, but they've told us not to distribute it anymore. So I won't be able to show you that one, but you can take it from me that the potential gradient calculations work as well. I also want to show for the next tool, one called Euler deconvolution. So it can determine the locations and shape index of submerged bodies from the derivative of the magnetic signal, as it says on this slide. And this can work on either magnetic or gravity signals. And it's now even possible with measured gravity gradients to do this sort of thing. I'll show you an example. So we have two tasks here. One is an isotropic example, and one's anisotropic. I'll quickly find them. So in this case, you've already probably seen some of the power of the task file language, but in this case, the viewer has been turned off in this task file. So I'm just going to quickly turn it on. And it's as simple as opening it as a text file, finding the bit you want to change. Just I'm going to quickly change this to true. And just like that, you can run it completely differently. It's a very powerful scripting language. So you'll soon see in a second. There we go. So these are the isotropic clusters, the clusters that have been generated from the Euler deconvolution. You can see all
Matthew, before you could explain what this pop-up is, they've never seen it before. What's this 3D viewer you're showing now?
So this is showing the it was the shape locations, the submerged bodies, I believe, of all what was measured from what was gathered from the Euler deconvolution. And I think there's more views coming. So this is further processing. So these are the, these spheres are the locations of best fit for all these different hits under the data set. And so it's sort of clustering these into single spheres to reduce the number of hits. And that's that one.
Sorry, and they're showing the depth to top of magnetic body or something, are they? Or what are they showing?
Yeah, I think that's what they're showing. Yes.
Okay.
Because in that previous view, the shapes, all the hits were really long and straggly. So that suggests that maybe it isn't an isostatic sort of. It isn't isostatic, and maybe it's isotropic. It should be anisotropic. So if you run the same thing but with an anisotropic instead to generate flat planes rather than like individual submerged bodies. So I'll drag this over here. So you can see that it's generated a number of hits and it's tried to fit a couple of different planes, I think 3 here, to all the different hits. And as the clustering proceeds, so it's iteration 1 of 250. So we'll proceed to 32 and starting to break up those planes into a larger number to see which is the best fit. I'll keep going. So 63, you can see it's splitting up those squares, all those different planes. Keep going, keep going. And then soon it will be done. And complete. So now it's got the final clustering result with all those planes that it was trying to fit, all the ones that it split up, is generate a single surface to give you an idea of the plane underneath. And it does have a bit of a dip here, but that's due to the mathematical model that is being used. So if I close that. So that was for a magnetic.
Just before you kill it.
Oh, sorry. Do you want me to run it again really quickly?
That yellow surface was the depth to basement best fit through all the Euler solutions.
Yeah.
With a gradient. It was a co-Krieged, geostatistically derived surface, which is a best fit straight below the DTM.
Okay, because what I noticed was that it was very smooth. Is there a way, and as you know, like in geology, there are very sharp contacts. And so you said that was like a Kriging to produce that depth, was it?
That's just a simple co-Krieging using, because you've got the, it's got it back again. It's just to fit through all of the solutions, and with a range, and you've obviously got access to range parameters and nugget effects and all sorts of things. It's a full-on geostatistical surface with best fit through those points.
Yep. So, so this is the magnetic case of Euler deconvolution, but it can also be performed on gravity, so on density responses. I've got that as well. So, oops. This one. So this is a so this is the same tool running on the gravity gradients, tensor gravity gradients, measured gravity gradients. So running. Just give it a moment while it's running.
Matthew, it's running on the phase of the tensor, so it's actually using Fourier transforms to calculate the first balance phase products, whereas sometimes you can just run it off the measured gradients directly.
Right. And that seemed to have completed. I don't know if there was. So the viewer was off for that one as well, so I'll quickly turn it on just so we can see it. So I'll save it. There you go. Okay, there we go. So now it's got the clustered bodies underneath. You can see all these little hits, all these little dashes. So that's that clustered, and then so from that it's generated these sort of spheroid shapes underneath the surface, and then so it's done a horizontal fusion of the clusters as well. Yeah.
Oh, and in that view,
Yep.
can you interrogate each point to see how deep it is, or?
I don't think you can interrogate them. This is more just for a individual view, but all the data sets are available in the output directory. So
Yeah, so you can just go to the database and.
Yeah, you can go to the database and find the data there.
Yeah.
So what is the viewer and what are the options for that viewer, Matthew?
So there's a number of hotkeys. It's actually based on the default VDK camera, and so there's a lot of different options you can rotate, and depending on what key combinations you hold. So this is control click and shift click pans and all that sort, and then just regular click rotates like this. And there's a bunch of different little key codes and stuff you can use as well, I believe. So it's basically the default VDK viewer, which is available online. You can find the hotkeys for it there. Yeah, and so that was the last viewer of that tool. It's completed. Yeah, so that was Euler deconvolution. I'm going to move on to WormE. So WormE can find structural trends using gridded potential or gravity field data. So it can find all that sort of thing from that. I'll show you an example from the Darling Fault. So the Darling Fault's one of the biggest geological features in Australia and most obvious. It's the example we use. Let me get the task up. So the Darling Fault worms, there we go. So we take a subset of the grid of Australia, and then even with a large grid size, we can see this sort of structural trends. I'll drag it over. So you can see that the WormE tool has generated a fault or something like that underneath here, and you can see all the lines that it's determined as hits from the magnetic data, the magnetic signal, and so that's available. I'll close that. That's it. Yep. So the task completed. It's got an output.
So Matthew, obviously there was some contacts for the fault and some dips estimated down the length of the fault.
Yep.
As well to pull that off, and then creating a 3D surface draped below the topography, which is what you saw, and then that's all saved off. That surface is saved off, and likewise you can look at that afterwards as well.
Yeah, exactly.
And yeah, that's for gravity. It wasn't magnetics. It's your slide is mislabeled. That's actually
okay.
It's actually
Right.
gravity.
Sure. Yes. Well, in that case, I'll go to the other task I have available, which is also is this also gravity, Des?
It's gravity gradiometry this time.
Right. Sure. So this is potential scalar. This is gradient potential. Sorry about that. So I'll get the Orozonia example up. So I'll run this one here. Okay, there we go. So this is from the Orizonia cookbooks. So we have all of these different little black lines are probably surface, not very important sort of worms to find. But then there's this white one here. That's an important one, measured as quite significant. And then it's got all these small little planes down here that is determined from the gradient potential, essentially. I think that might be...
It's also doing dip determinations.
Yeah. And so it's got, it's got some outputs as well. And so you can, like what I did with the Naudi, you can take in those, you get to write out those VDPs, I believe, and show them all on the, show them all using 3D Explorer or a similar tool. Yeah, I think that was it for Worm E. So the last tool I'm going to show is MagTransX. So magnetic transects is based on the match filters that were shown in the grid filter training. That was the very first iteration of it. The spectrograph theory is based on ensemble of bodies at depth. Basically, this is the inverse of the random dipole forward modeling in a way. And the algorithms we use in MagTransX are originally in a paper from Roger Clifton. You may know him. And basically determines the susceptibility of, it determines hits underneath the, at depth from magnetic data. And so I'll show you a task of that. And it's all based on the Fourier transform method. Let me try that one. This one here. Try this across.
With this one, you've shown everything just using the outputs and not the GUI. So perhaps you should come back and show the GUI in this one as well.
Sure. Yeah, I can come back to that. So I've got 2 windows. So this one comes in 2 windows. So you can turn its GUI on and off if you want to run it in batch or anything like that. But this is showing the, let me just make this a bit bigger. So you can see that the hits determined underneath the depth of the data set along here. And you can select the individual stations to see the power spectrum that you got, and then therefore the depths that were predicted. This red line being the cutoff for that, for the noise criteria. And this is all output as a vox set. So if we close it, finishes up. There we go. So the vox set is this one. And I'll quickly just show that in 3D Explorer. So this vox set display is pretty different, been changed a fair amount. So I'm not sure exactly. I think, oh yeah, so essentially what's happened here is the, because it's a geodetic grid, oh wait, sorry, the scaling's off is what I mean, in the height direction. So because it's, it's tens of thousands of meters long and it's only a couple of 1,000 meters or so deep, it's come out very flat. So if I make this maybe 100, so that works. Okay. Well, in this case, it isn't going to show me that, but you can see all the hits are here. It's just all in the wrong scale, essentially. But yeah, and you can slice through the vox set. So you can take cuts through to see inside, and so you can see all these hits that were there along that line. Yeah, and that's the vox set rendering we have now in this tool. And I'll show you the GUI that Des was talking about. Task. So we have a Java GUI that can help you build your task files, and we've got one for just about every tool now. So this one's the MagTransect one. As you can see, it's loaded in the task and it's found this line. So you're trying to do a single transect across this part of your data set. And then you've got all your parameters in here that you can select and change. And if you want to save the task file, you can just save it out. And you can use it to edit your task files on the fly, and you can run it directly from here too.
So demonstrate the changing the transect angle and designing your experiment.
Sure. So if you wanted to take the transect to be at 45 degrees or something instead, relative to north, you can do that, and you can move it around with the spinner. make it longer or shorter, fit it within your data so you can examine any area you like. That's a pretty new feature in Make Transects. Originally, it was just either north, south, east, or west.
A couple more lines.
Yeah, no, yeah, just add some more lines as well, sure.
If you're an interpreting geologist or geophysicist, you wouldn't go along the strike, you'd go across the strike. So your angle's wrong by 90 degrees.
Sure. Some more like something like that. And move across. So yeah, you can use this sort of tool, this GUI, to manage however you want to change your task file. Essentially, yes. And you can change your FFT power spectrum options. You've got all sorts of different little options that have been developed to change the way that the FFT is done and other parts of the algorithm. I think that's pretty much it for this part of the presentation. I'll probably pass over to George, but first, do you have any questions?
Yeah, can I ask about the magnetic transects?
Yeah.
So how do we get to there from the project manager options? Where is it under?
Through here, through
yeah.
here. So it's under modeling, magnetic transects.
Okay. And then with the output, so it came out as the voxel.
Yeah.
And I'm just thinking about how you could use it. Like, can we export it so it's just the one surface, similar to how you did the Euler anisotropic?
At the moment, I'm afraid not. You can get it out as a CSV, but that's also in a voxset sort of format. It doesn't export as a surface or anything because it might determine multiple surfaces or that sort of thing. So yeah, at the moment it doesn't do that, I'm afraid. But you can open that same voxset file in other things like ParaView and other viewers like that. So any other questions?
Yeah, that similar question for where that Euler deconvolution builder was.
Yeah. For where it is.
Yeah, sorry.
Let me just check. That's a good question.
Oh yeah.
Sorry, there it is. Yeah. And it might even be, it's under magnetics as well.
Yeah,
so
no worries. All right, cool. Thank
you. No problem.
I think our current version is licensed for it though, Liam and Adam. We might have to get we might have to get a trial version or something and test it out.
Oh, okay. Yeah.
Cheers, James.
So on that particular point, we just learned a minute ago that all of the next 3 years licensing has been approved and paid for by GA, and so therefore that includes all of this material you're seeing today. All of the users at GA have access to it because that's what the licensing includes. And you don't get this technology unless you move up to the version 6.1 or the 6.11 and all this sort of stuff. Yep. So you're supposed to have all that installed and licensed on your laptops already, but there's been the usual delays, I believe.
Yep.
Fantastic. That's good to know. Thanks, Des. Yeah, I think our license will be renewed in, 4 days. So, yep, good to know.
All right.
As for query, of course, all the damn data's there. We just chose to put it in the box set, didn't we, Matthew?
Yeah.
For purposes of trying to have an efficient, compact way of getting it there. Unfortunately, we haven't been able to pull off the transparency. All the null values still sort of show up, but we're hoping to. The underlying GPU toolkit's not up to it still, even though we thought it would be. Bit of a pain, but that's the way it is at the moment.
Been a bit of an ordeal trying to get that working at the moment, but it might be development soon, maybe. We're lucky.
Yeah.
The underlying toolkit. Yeah. So, is there any other questions anyone had? If not, I'll go and hand over to George. I'll just let him know that it's ready.
have a couple of minutes break.
Yeah, just be a couple minutes break and get a coffee or whatever you like. Just be a sec. It's all set up. Welcome to this. So it's presenting on the left. Well, it's screen sharing on the left one at the moment. And I think the mic and camera are on still.
Okay, so Matthew was running in here before me. Is everybody just here? Hopefully everyone's here. I'm just going to be going. Okay, also waiting. It's good. So yeah, I've got two topics today that I'm going to be going through. First one of which is it's a new tool. It's the equivalent layer reduction to the pole tool, and we'll also be going through some of the clustering tool options that maybe Matthew didn't quite touch on, and just some other use cases for the clustering tool. So yeah, I'll just jump right into it. So basically, yeah, two topics here. So with the equivalent layer tool, mostly, I'll just bring you into it slowly. We're just going to do a quick, intro, some background knowledge on what the RTPs are used for, and why this second sort of option for performing an RTP could be useful. And then I'll sort of start to go into detail about how it works and just the sort of results that you might expect from it. And then after that, I'll be going on to the clustering tool, talking about the different options for that, the isotropic, the anisotropic, and the tensor clustering. So let's get into this. So of course, RTP stands for reduction to the pole, and basically we're using this technique to change an observed data set that was measured with a certain inclined magnetic field, and we want to reproduce the signal as if the data set had been measured where the field was vertical, so at the pole. Now, the reason that you want to do this is to make sure that the bodies that are underneath the surface are actually located underneath the anomaly that you've measured. So it's sort of an aid for interpreting the data set, because you know that the signals that you're viewing have originated from directly beneath those the anomalies on the observed data grid, assuming of course they're not like a remnant body or something like that. But generally speaking, we're using the RTP just so that we know exactly where the causative bodies are underneath our observed grid of like the magnetic field. So just like as a quick demonstration of this, on the left here, we've got the 90-degree inclination. So the magnetic field's running vertically here, and we've got a single source that's in the middle of our grid here, and it's clearly producing a symmetrical response, that bullseye pattern that we see here. And then, as you can see, when we change the inclination, so here we're at 45 degrees, we start to get a sort of a shift. You would think that it's almost as if the body has moved, up vertically along the ground almost. But really, it's just because of the inclined field that we get this sort of tilted response. It doesn't really line up with where we'd think the actual body is underneath the ground. And then, as you can see, as we go to inclination of 0 degrees, the effect is quite more dramatic, and we would honestly have no idea. Well, unless you were looking, specifically for these sort of signals, you'd think that there's almost those two bodies there creating this magnetic field. So, yeah, basically, what we want to do is we want to take these harder to interpret images and bring them back to something that's simple, so that we can, evaluate the grid, evaluate our data sets more efficiently. So, generally speaking, the easiest way to do this would be using a Fourier transform method, and that's what Intrepid has been doing mostly for a while. And this is probably, this is perfectly okay, as long as the inclination isn't too low. When the inclination gets closer to 0, you start to get these large streaking or artifacts in your output result grid. So there's quite a, it's really not necessary unless you're looking at data sets that have been gathered near the magnetic equator. So or areas where the inclination is, at the equator, magnetic equator. But generally anything below or above about 20 degrees inclination would be totally fine. Just use the Fourier domain method. So here's a example. This is a data set from Mali. And you can see how, I'd say the inclination here is roughly around 3 degrees. And you can see how there's vertical streaks that have sort of been introduced into the result, simply due to the breakdown of the method as you approach an inclination of 0. So there are some options that you can use within the Fourier tool the grid Fourier transform tool that will allow you to like sort of mitigate some of these streaks, but that will come at the cost of the reliability of like the amplitude or the total signal strength will be slightly reduced, so it won't be as reliable. So, you know, you're presented with this issue here where if you want to get a good reduction, you're not going to have the correct amplitudes over your anomalies. So, or you have to deal with, obviously, these quite bothering streaks where the noise has just caused, yeah, all these artifacts to appear. So the equivalent layer method is using a spatial convolution method, so it doesn't have this issue as you approach 0 degrees. And I would say actually that this tool works better when you are at the low latitudes, but as you get to the sort of the moderate or intermediate latitudes, it's really not that effective. You'd be much better off using a Fourier transform. So here we've just got a very rough sketch of a sort of like a line response as you fly over an anomaly where the magnetic field is at 0 degrees. So we've got this unknown body and it's causing this classic, you know, dipole, well, like a lying down dipole field, which we could see if we just go back to here, this inclination at 0 degrees. So it's as if we've taken a line, like a flown a line straight from the bottom all the way to the top. And that's the sort of signal that we're observing. And now, if we had a noisy data set, then it would be quite hard to actually reduce this to the pole signal. So what we can do is, well, say the first sort of concept that we're going to be using for solving this issue is we want to model all the surface or all the objects that are below the surface that could produce this response. So we're effectively doing almost like an inversion. We're trying to guess what sort of structure underneath the ground could produce the signal that we've observed. So we actually create a grid of sort of magnetic strengths or weights underneath our observed grid, and we will be using forward modeling to recreate the observed signal and adjusting the weights of the magnetic sources underneath our signal in order to best fit the observed response. And then when we get this model, we'll be able to then recalculate the magnetic field or the observed signal at any inclination that we desire. So here we have, you know, just roughly, I can say, just to give you an idea, we've created a number of individual little sources, and what we're going to be doing is using convolution, like a Wiener filter, and using convolution to actually estimate what the weight is for each of these sources. So the Wiener filter is effectively just modeled off a single plate that's been had the response calculated for it at the inclination of 0 degrees. So we can actually see that if we go back to here, we'd be effectively creating this snapshot, and we'd be trying to create a Wiener kernel that will fit this response to a source effectively. So what we'll be doing is we'll be windowing, and we'll be running through the entire grid, estimating each of the equivalent sources, and that will build us a grid underneath our, effectively it will build us a model that we can then create a forward model from at any inclination that we care to solve for. So if we now do our forward model with the inclination at 90 degrees, we can produce a sort of more closer to, we should be able to get our effective our RTP grid effectively, because we've created a model that will produce the other, or the inclined grid. We'll be able to produce this vertical magnetic field grid as well. So hopefully gives you sort of an idea of what we're doing. In general, the workflow is a little bit like this. We've just got our input magnetic grid, and we are using our Vena kernel that we've calculated to convolve, and we're creating an equivalent source grid. And then from that source grid, you'd be able to either just run a forward model on all those elements and get our output grid, or what we can do as a sort of a tuning or an iterative process, we can actually go backwards and we can use the forward modeling to reproduce our input magnetic grid. And then we can compare the differences between what our equivalent source produces as an observed grid and what the original data set was. And we can take that further and effectively we can take the differences between what our forward model produces and what the original grid was, and we can convolve those differences with the same Vena kernel and produce an adjustments grid. So we'll find out exactly which parts of the equivalent source grid weren't actually accurate enough, and we'll get a sort of like a subgrid or an alterations grid that we can then add back into our equivalent source. And you can actually repeat this process a number of times to try and narrow down and reduce the error between our inclined forward model and the original inclined data set. And then at the end, when you approach the a best result, you can then take our forward model at 90 degrees to get that RTP grid. So here we've got a synthetic example. This was actually created in GeoModeler, but basically we've got a couple of sort of oblong or roundish shapes, and these are our magnetic bodies underneath the surface. And we've just run a forward model at 90 degrees inclination and 0 degrees inclination. So I guess you could say that this is our our ground truth. This is exactly what we would expect to see, field at a vertical orientation. However, because of where we've measured this grid, we've actually got this inclination at 0 degrees, and it doesn't look anything like what we would want to be interpreting. So we've got this dipole, sideways dipole response here. There's two bodies, and what we want to do is we want to apply our new equivalent layer tool to try and fix this and see how close we can get to this original result. So the tool itself is a GUI underneath magnetics in the project manager. If you go to magnetics, you've got the equivalent layer tool now. You can just open that up. I should probably get rid of that so we don't open up a task file with it. But yeah, so this GUI, there's a few little things that we can talk about here. Obviously, we've got our input source grid. So this is our magnetic data set. And we will have a few options what we want to do to this grid. We can detrend it. It's recommended that you do this so we can get rid of any sort of shifts in the signal from across the entire grid. But basically, we've got an input grid. We've got the IGRF, so the magnetic field, so the information about what the magnetic field was doing at the time of the creation of the grid, or we can manually specify the angles that we want to use for the grid, or for the magnetic field that we want to reverse the, or that we want to transform from. We've got a depth control over where we want to create this virtual layer of magnetic sources, and then we can specify the size of those sources that we're going to be using to create the Vena kernel. But a lot of these options will sort of self-tune, so you don't need to worry about them too much. So we'll go back to the presentation, and this is just sort of outlining the options that we're going to be using for this first first pass at the problem. So after the initial run, we end up with this as our result, and this is like the raw output. So we've taken that 0 degrees inclination grid here, and the result is, you know, it's moderately close, I'd say, to the ground truth, which is the, of course, the forward model in GeoModeler. So, you know, it's a decent result. We do have a bit of streaking, or like corrugations here and here. So I'll just be quickly going through some of the options that we add in to sort of combat this. So there's the decorrugation tools. So this is just harnessing the decorrugation tool from that you can find, you know, under leveling decorrugation. So it's just using that to try and reduce some of these artifacts in the output. So that's used in the exact same way. You do have access to all those options over here in the decorrugation or the convolution artifact filters panel. So we can, if we want to, we could set up these parameters to match here, and we should be able to get a better result. The reason we've got all these corrugations is just it's just a byproduct of the Vena filtering and the equivalent source grid that it produces. It doesn't really, you know, it doesn't look as clean as you would imagine. So when you do the forward model on it, you do get a little bit of streaking in the output. So next we've got this is just to show you how it compares to the Fourier transform method. Because we've got a synthetic model here, there isn't a lot of noise, so it's actually not hard to use the Fourier transform method as well on the data set. You do get a little bit of, you know, edge effects and things like that, but overall you can use the fast Fourier transform method when you do have this sort of perfect response or very low noise data set. So yeah, at the left here we've got the just a regular Fourier transform result. And then we've got the low latitude correction, which does deal with a bit of that, some of the edge effects in some of the spots, but yeah, it does actually affect the grid quite significantly. And then we've got the equivalent layer method on the right here, which is, you know, quite comparable, I'd say, to the low latitude correction. So the other artifact filtering options you have, there's a de-ringing ability. So this is some high frequency noise that does make its way into the output grid. Again, due to the kerneling, or how we apply the convolutional kernel. So you've got a high frequency decorrugation tool effectively built into the RTP method. So you can see the sort of vertical streaks here, and they've been mostly neutralized in the output. So this is just some extra tools you have built into the equivalent layer tool to hopefully reduce or to improve the quality of the grid, really. The last step, where I was explaining before, we can iteratively go through the grid and try and get a better result each time. So we actually, when we recalculate the grid at the original inclination from our with the forward modeling, we can take the difference between that original grid and our calculated grid, and we can calculate the error between them. And then we can try applying the corrections grid to try and reduce that error. So if you look closely, you might see some slight changes in certain areas of the grid as it goes through each iteration. And effectively, we keep track of the error and see if we're actually improving or not. And then when the improvements stop, we can actually revert and go back to the last the lowest error grid and use that as our model effectively. So I'll just demonstrate how you actually use this tool for a little bit. So we've got all these examples for it located under the cookbooks area. We go to the magnetics tab under cookbooks and then go to reduction to the pole and look at the task files. We've got a number of tasks here, and you'll notice some of them are FFT tasks and some of them are equivalent layer tasks. So this is just to give you sort of a comparison between the two methods. So we can start with the Mali task file. So just to give you a quick idea of what the Mali grid looks like, we can open that up. So again, this is at roughly 3 degrees of inclination, the magnetic field. And we can see some of these sort of dipole responses, like at the inclined dipole response here. So a sort of anomalies like that, things that we might want to resolve from the using the RTP tool, just to get a better idea of what they look like. So we can just go back to the task files here, go back to that equivalent Mali equivalent layer RTP task, and we can open with the task file, and this will preload our GUI. As with a lot of the new tools, we can just open up the task file and see all the settings that we're going to be using and make alterations if we care to. But for now, we'll just run this, and we should get an output reasonably quickly. Okay, so here's our output grid. We can compare that quite quickly to the input. We want to just copy that into here. We can do a quick comparison. I'm just going to use the R3 Export tool to do this, use separate views. Yeah, so we can see that I just want to point out again, the detrending tool is going to deal with this, you can see this sort of shift as you go from the south to the north of the grid. So this sort of linear trend can be, is going to be removed by the detrend option, which I can show you again. So we've got detrend options here. We can turn it off completely, or we can do a, depending on what order of detrending we want to do, we can choose that. But generally, just leave it on the linear transform. So, we got sort of, just to give you an idea of the options we've used here, we've set our sensor to layer depth to 400. Now, this layer depth option is quite, it can require a bit of tuning or estimations, but generally you want to make it significantly larger than the cell size of your input grid. So you'll notice I've included the cell size of your input grid up here at the top. That's just so you can use that as a reference when you're trying to specify the other parameters in your for the RTP. So the Vena kernel is also set to the same cell size, and I'd recommend honestly just using the exact same cell size as your source object. This seems to give the best results that I've seen so far. And yeah, we can sort of just say, in this case, we're not doing any iterations, we just left it at 0. We have an increment multiplier, and that's just how much of the iteration suggestion do you want to actually apply to your new grid. So it's sort of a way of more slowly approaching or more slowly applying the corrections that the iteration suggests to use. Basically, we've got the controls for the IGRF. In this case, we've got a grid that's geolocated, so we can use the automatic IGRF controls. As long as you know what year the grid was created in, that should be fine. you can see how it's updating the inclination and declination automatically. And yeah, we're not using any decorrugation. We are using de-ringing though. So yeah, that's just basically that's everything you need to know. If we want to compare how that would run to the fast Fourier method, we can just go back to Intrepid, and we can open up that FFT task here and open up the grid filtering panel. I'll just quickly show you how the so at the moment it's at a low latitude. Might not say it. We can just make sure that's on exact settings we want. So this should introduce, you know, quite a lot of streaking, as you can see. But if we do turn on the low inclination option, then we should get a better result using the Fourier transform. Yeah. So we've got these, you know, there's two ways of approaching this low latitude RTP, and the equivalent layer is sort of just another tool that you might want to use or try out at least to see if you can get better results. You might, you know, it might be useful to compare how the amplitudes are affected and whether or not you can get away with using the low latitude options. But yeah, that's basically everything about the equivalent layer tool. Probably been going for that pretty quickly. So does anyone have any questions about how you use this or how the tool works, or any questions about it?
Which method have you found to be more accurate?
That's a good question. You know, I would say that the equivalent layer method is more accurate if you've been forced to use the low latitude correction in the Fourier transform. Then I would say then you're better off using the equivalent layer tool in terms of the amplitude accuracy.
Okay.
Yeah, but you know, it can be slightly hard to tune. So it's definitely a good idea to, if you want to try it on your own grid, just have a quick look at the examples that we've got here. You know, just to try and give you a head start on picking the correct parameters. That's all.
Yeah. Okay. Yeah, so it'd be a good idea to run that low latitude in the normal FFT area to see roughly what you should get.
Yeah.
And then you run the equivalent layer tool, thinking that that's sort of where your end goal should look like. Yeah. Okay.
Yeah, I'd say that's probably, you know, one of the better approaches to it. Yeah. I was thinking of something else to mention. Yes, so if you wanted to, there's actually quite a few different approaches to the equivalent layer method. And the one that we're using here is actually, it's based off a paper by Peter Gunn and Richard Almond from 1997. So if that's the, if you want to go look at the literature behind this sort of tool, that's it's actually following that methodology. So I believe there might be actually a reference to that in the help menu. Yeah, so if you want to read the paper about it, you can just take a look here. That sort of goes into a lot of detail about, you know, the how effective or how it compares to a traditional method. So yeah, if you need, that's always
okay,
a
cool.
good source
Yeah,
to have a look at. Does anyone else have any questions? Okay.
Just a general one, it's not related to what you presented, but is there a tool in Intrepid for normalized source strength?
Ooh. I'm not sure. I'd have to, I'd probably need to get Des to handle that one. Don't know if he's listening at the moment.
Yeah, no worries, it's fine. chase
I
up
am
later.
here. Yeah, no, the normalized source strength is much overrated. Let's just put it that way.
Okay.
Remember, I was David Clark's examiner, and he's the one who cooked this up with NCOM and all the boys out of Sydney. There's much more to the signal than just the normalized source strength, and that's, you know, why pick on that one? Why not the Frobenius norm, the second invariant, the square root, and the cube root of the third invariant, and all the rest of it? It's to try and reduce it down to one thing when you get into magnetic tensor components is trivializes things, and I don't put much store by the NSS myself, given the many different ways of looking at what's in the signal, and to sort of somehow say that you can convert TMI into NSS and somehow you'll get some other insight. You know, give me a break. Sorry, I'll just tell you straight.
No, that's fair enough. Thanks, Des.
It's a beat up.
Well, thanks, Des. Okay. Yeah. So if anyone's got, you know, if you're having trouble with the tool, again, just have a look at the examples. There's quite a few here. Just anything with equivalent layer in it will be a good, you know. We've got this synthetic model here. We've got some other grids. So hopefully, yeah, you should be able to figure out all the settings from these examples effectively. Yeah, otherwise I'll just move on to the second half of the presentation. So that would be the clustering. I know Matthew went through a couple of the you know, functions that the clusterings are performing, at least for the magnetic tensor data sets. But I'll just be giving a more general look at how you use the tool. Some of the things it can be used for, like you know, clustering of point clouds and finding like faults within seismic data sets and things like that. So, and also there's a bit of stuff you can do. Another application is using it to calculate tensor dips along sort of fault lines within tensor gradient or gravity gradient data sets. So, you know, just back to the basics, the sort of the first thing you can do in the tool, just really simple, finding cluster centroids. If you just want to thin out data, or, you know, you need to just estimate the rough location of the cloud of points, this is the tool you can use. It's just going to save a simple data set with all these centroids and the qualities of the each cluster, such as, like, you know, how many points has the cluster got, and what's, you know, where it's located. So really simple. You got a few options to use for this tool, just like, you know, restrictions, how many points do they have to have, and how far apart can the points be, and sort of like the circumference of the cluster, and whether or not you want to, or how much confidence you have in each cluster. So it will selectively, you know, eliminate clusters that sort of overlap with other ones, things like that. I can just give a quick rundown on how you can do that. Just, we've been using a data set here. It's a fault. It's an aftershocks data set. So it's sort of like, it's got little, it's got positions of the sources or epicenters of after an earthquake. It's got all the afterwave epicenters effectively. So those sort of locations can be used to sort of infer sort of like the fault structure underneath the ground. So we just go under examples, tasks, and into the anisotropic clustering. So we've got our Landers earthquake clustering task. I'm just going to use this task file just to give a head start. it's actually on anisotropic at the moment. What we're going to be doing is some isotropic clustering. So I'm going to change that using this tab here. And basically, we've got our input grid or input database up here, which has got X, Y, Z points in it effectively. We've got a few options. You know, the coordinate, the convention is you know, east, north, downwards, positive, things like that, our data set. And this distance units here, which actually refers to the, if you have a data set like this, where the depth distances are quite large, you're actually in kilometers, not in meters. So that's what you use kilometers for. But you most typically probably be using meters as your distance units. So we've got the settings here. If we just want 10 points separation, we might drop it down to 20 kilometers, and perimeter might drop down to 10. We can just run that real quick. So it's got all these like overlapping clusters. So we just continue, see if it resolves some of those, and it has. So this sort of window that pops up is just giving you a visual indication of how the clustering is going. We can see that it's we've probably put too harsh of a restriction on it. It's not really picking up maybe some other points that we'd want to get a cluster center for. So we might need to reapproach that. Maybe just loosen up some of the tolerances. Perhaps it will find some of those points. Yeah, it's sort of just a iterative process. Maybe we'll go the other direction actually. But yeah, this is just, we can, you know, try increasing the confidence that hopefully we don't cull as many of the clusters. Yeah, so yeah, that's just the basic isotropic clustering. It's just used as a starting point by the other tools, but you know, we figured we may as well expose it to the users. And if they want to use it, they can. I'd say the real useful part of this clustering tool is finding sort of 2D structures within these point data sets. So in this case, we've got seismic epicenters. So if we fit a sort of a 2D plane to those points, then we can effectively use that as an estimate of where a fault may lie underneath the ground. You can also use this if you just want to build a sort of a surface from like a LiDAR data set or a radar data set. If you've got a lot of points and you want to thin down all those points just to the fundamental surfaces that they represent, then you can also use the clustering tool for that. So part of the process is that it's going to be splitting. It's going to be fitting a plane to all the points, and then if it exceeds the certain amount of tolerance, then it's going to split that plane into separate smaller planes. So we're going to be setting up a job here that will target a certain amount of uncertainty in the data set, and it's going to be fitting, like, you know, iteratively just going through splitting up all these planes and trying to figure out which ones to keep and which ones to try and split up and adjust further to sort of, yeah, find all of these planes within the data set. So you're going to have control over how, you know, how coarse or how fine you want this to be. We can have a quick look at this. We'll reopen this land as earthquake clustering task. This is the and we're going to leave the stock settings for now because it's on anisotropic, which is what we want. So we've got a limit here and a number of iterations, so 12, and things like we've got our uncertainty. This is our tolerance that we're trying to shoot for. Some other options here. This is just to do with the reporting. It's not necessary, but you'll be able to go back and look at the actual numbers or the how it's trimmed through all of the different suggested planes that you've created. And there's some other restrictions. So if we want to, we can actually cut off anything that exceeds a certain diff angle. And there's some other checks that we can perform. So if a cluster doesn't fit correctly and we've already reached the end of the iterations, we can get rid of it completely. So there's just you don't need these at all. They're just optional things that might help speed up a workflow if you want to get rid of maybe some noisier results. So we can run that, and it's actually going to step us through the iterations depending on what our reporting frequency was. So at the moment it's 5, so we should get every 5 iterations a new display of where it's at. You're free to maneuver this model here just to get an idea of what it's actually trying to do. You just kill the window and it's going to go. It's already jumped ahead 5 iterations. It's on the 6th iteration of 12 now. And you can see how it's progressed. It's highlighting the old planes in blue and the new ones are in purple, just so you know which ones have been discarded and which ones have been added in. So we can kill that again and we get the final result. So these planes here are trying to, fit those points. And I think it's done, pretty good job here. Maybe if you go a bit further, so if we wanted to do that, what we have to do is increase the number of iterations. We could do say like 50 or something, just increase the frequency of the reports so we're not here all day. We'll try running that again, and hopefully we'll get a bit of, okay, so see how it's finished already. This is because it's already satisfied the tolerance requirements. So we can kill that and we'll just drop the uncertainty requirements. We try 2. It should go for a bit longer now. So yeah, it's still going. We're 11, 21. So maybe we've gone a bit too coarse and it's sort of devolved into a bit of randomness. So we obviously took that too far. If we want to, maybe we'll just go back to about 3 and try that. So yeah, again, it's just a bit of a process, but you should be able to tune the results to whatever your requirements are. Obviously the grid, it was set up to work pretty well initially. That's why the uncertainty was at 4. So yeah, that's really about the result you'd want. If you want to take these planes and you're going to incorporate them into a geological model or something, you could use these, the centroids and the dip and the strikes that are exported to create your sort of contact or your interfaces in your model. Everything for the anisotropic clustering. So the final topic is going to be on the tensor clustering. So basically what we're trying to do here is we're taking the Euler systems of a tensor gravity gradiometry database, and we're analyzing the solutions for areas where there's a tendency for a two-dimensional, or there's a two-dimensional sort of structure. So basically we're going to be using a different tool initially just to create these Euler solutions, and then we'll be using the clustering to see how they fit together and to produce a strike for the faults within the data set. So if we go into this a bit deeper, so here we've got a, how's our tensor grid? It's a gravity data set, and on the right here, we've got a eclipsed data set. This is just showing the points where there is a very small middle eigenvalue. So effectively a 2D, the eigensystem tells us that there's a 2D structure here. So these points are actually what we're going to be clustering. And we'll be using those, the result of that to then query the original data set again and figure out what the dip angle is for all these faults that we're trying to identify in the data. So if we have a look at that, this is the output. This is the output window that you would see when you're running the tool. And you've got all these small points here, the eigen system solutions. So we're actually just running on a small subset. Keep that in mind. And we've clustered those to find sort of profiles within the eigen systems. And then we're querying the tensor grid at these locations to figure out what the dip angle is. And the dip angle would be represented here by the tilt of these diamonds in that window. So I'll just bring up that example. It's actually in the cookbooks area. Scroll back up and go to the tensors and yeah, full tensor. Go to Montezuma. So we've got a number of task files here and an interpretation. So I'm going to be showing you the 3 job. This is already using some pre-computed eigen systems, but we can do those. We can figure out those manually as well if we want to, using the previous job. So we've got there's 2 tasks here, number 6, number 7, and they're sort of part of the same workflow. So number 6 is a convolution filter. So that's what's calculating our eigen systems, and it's also going to be doing a culling of the data sets, so we only get the important eigen solutions that are, the ones that suggest the 2D structure. So we're filtering out everything else already when we run this task. So let's open that up just to show you what we would be doing using the convolve tool, and that's operating on our tensor data set, and it's producing our eigen system solutions. So this is what's going to be going into our clustering tool. And those values should be called, yeah, the Montezuma 2D bodies. So this file here, and that's, yeah, as we saw before, these are all the areas with the 2D structure where there's a strong tendency for a 2D structure to appear. So when we run the actual task file here, it's referencing a pre-computed file, so don't worry too much about that. But we can execute this something like this, and it will show us. So it's done an isotropic clustering. So it's, again, as I was mentioning before, the isotropic clustering is like the starting point for the clustering. So we don't really need to worry about that. It's just showing us all the steps. Now we're doing some. It's thinning out the clusters effectively, seeing which ones are actually should be merged together. So just a couple of steps of that. And then now it's calculating the dips. So it's effectively in each cluster, it's got a profile or a strike of each fault. And that's what the eigen systems we use to find. And then we're using the tensor data set to query what the dip angle should be. So all these little plates here where we've decided that there should be a fault line. The grid that you can see that it's all overlaid over is actually the DTM. So if we go back to the Intrepid project manager and we just have a look at this task file in the actual GUI, it's going to show us that all the things we've loaded, and what we want to see here is that we've got the DTM grid here loaded, and we've got our input database. So this is the eigen system solutions. This is the DTM, and that's been visualized just as like as an aid, so you sort of know where you are in the model. And additionally, we've got the tensor database here. So it needs to have. It doesn't need the DTM, but you will need the eigen system solutions and that tensor database in order to run this task. So yeah, hopefully those results line up with what we'd want. I'll just go back to the presentation. So what the output of this task is actually this fault centers Monza directory here, and these points have you know, fields attached to them that are sort of the parameters of all these fault lines. So we've got the tilt, or the dip, and the dip direction, as well as the strike. So these are just sort of definitions of all the contacts or faults in the that are suggested by the tensor dataset. And you can see how I've overlaid those here, just along the strike direction, just so you can see where they correspond to within that subset of the input dataset. That's pretty much everything for the tensor clustering. So I assume if someone's going to have some questions about that, just go ahead. If you've got any questions. No. Okay.
I was just going to say, it's pretty cool how you could see that syncline when you're rotating it in the 3D. So all the sort of dips were coming up together at the top, and
yeah,
that was good.
Yeah, I think it's a pretty powerful tool. I guess the idea is you're trying to reduce the workload so that people aren't trying to manually interpret, you know, the data and try and figure these things out. Instead, you can use the tool to sort of, you know, highlight areas of interest a bit more rapidly. So
there's a lot of brand new physics here that hasn't been seen the light of day almost. George just brushed over it, but the tilt's also there. So any horse box tilts, if it's a 2D flat surface, the gradiometry actually predicts that below the surface what the average tilt is of all the blocks. And I know the hydrogeologists get pretty excited in GA about trying to figure out what the continental tilts are and all the rest of it. And yet there's almost no attempt to try and measure these systematically, and yet blow me down, gravity gradiometry just does it. And yet it's almost completely ignored that gravity gradiometry can be employed to look at regional tilts, especially when it's not on the surface topography you're talking about, if you're talking about groundwater tilts and things like that. So it's a whole new area of mapping which has never been recognised.
Okay. Well, thanks, Des. Yeah, unless anyone has any more questions, that is that's the end of the topics for today. So yeah, if anyone wants me to go back over anything, I can do that. It's fine.
Yeah, I think all the other stuff's been handled, George, the task files and the documentation and the process. You are mainly just concentrating on introducing some new tools, and I think you've done a good job with that. So, good out.
Okay. All right. Well, thanks for everyone for attending. There'll be one more training session happening on Monday. It's to do with some forward modeling and some random dipole topics. So hopefully you can join us for that. Otherwise, yeah.
Thanks, George and Des.
Yep, no worries.
Yeah,
Thanks,
thank you very
George.
much.
Thanks a lot.
Thanks very much for all that.
You're welcome.
Yes, very interesting. Have a good one.
Oh yeah, you too.